This is Math 20, and we were listening to, and we were doing some announcements in here, so help me out, Jonathan.
We were listening to Sentimental Lady.
And was Fleetwood Mac?
Yeah.
Okay, Fleetwood Mac, Sentimental Lady. And we'll close with something perhaps more appropriate as we close out today. I've returned the quiz to many of you, and that was the repeat, the opportunity to improve a grade, and the highest was 11. There were 11 properties. And some of the things, we did have our meeting yesterday, which is why Brian was in here today. We had our meeting yesterday, and part of my concern, and I didn't anticipate that this morning, but part of my concern was that I thought there needed to be a greater level of support for what we're doing. And so one of the things I asked for was what we had talked about earlier, the idea of the lunches afterwards on Friday, and that's being covered now. And part of my concern was, and I think that will change for some of you, but my understanding is that I think there will be fewer limitations in terms of your being able to be here on the Friday tutorial. That's going to change. And so the concern, and it comes down to simple for me. And as I said in the meeting yesterday, because of schedules and because we are 14% in growth right now at the college, we planned for 2%. We're 12% over and no extra funding for the growth. That translates into programs, instruction, classes, loads are going to be reduced in the fall. And as I see it right now, there won't be a way that I can do a Math 20 for next fall. This was on a very special arrangement. And so as I said yesterday, this is the one shot, one time only, to make something work. And you're part of something that I'm hoping we can hold up and say at the end of the semester, this worked, it's the way to do it, and a model for what should be done. Now, my load is such that you're the only group that will probably have that option in 4 years of the program. So to that extent, as special as last semester was, you've got to make this happen for you this semester. There is no alternative. It's not the thought yesterday was, well, if we do some things, we learn about it, and we'll do better next time. No, there isn't a next time. It's now. And so my commitment is very strong in that way to try to make sure that we get there, that we do well. And I made some very definite statements yesterday in our Ridge meeting regarding that and what I thought needed to be done. I think there was maybe a little bit strong coming in today, but the message is there, and that was one of the things I was concerned about, that there wasn't that kind of involvement. And if we're going to do this as a group, then we need the same kind of commitment, the same kind of involvement to make it happen this semester. And so that's what that announcement was. It was a response to my conversation with John Martinez yesterday, of where I felt we needed to have more support, more support for the program, and what, if we're going to make Bridge, where it helps you and is a special thing, then that needs to be supported. And so there's two sides to that. One is, okay, here's what we're trying to do, and I have expressed the concern that, where we really looked at attendance, we really looked at things last semester constantly, that hasn't been happening this semester. And so that was the concern. Now, some of the things I talked to you about yesterday, again, at the end of the week, you're supposed to have your homework such that Rita can sign off, and it has to be done before I can give you credit for your quizzes. Your quizzes count as 100 points of your grade of 700 at the end. That's roughly 15%. And part of the problem we have with our meeting at 9 to 10 is the setting for that, having that. So it's hard to have the group dynamics. When you're in the library, I expressed my concerns about that yesterday. I know that's a problem. Now, again, I'll get to your comment in a moment, but the concern I have is in the computerized homework, there's both positives and not so good positives. In a sense, to make sure that you are motivated to get it done at the appropriate time, I put deadlines on it. Now that gets in your way if you have problems that occur and to try to make that up. So in trying to respond to that not only in an individual basis, but across the board, if you have something that's occurred, this could be everything from problems with the job, problems with child care, problems with the car malfunctioning, Murphy's Laws, in effect. Things can go wrong, and they will. If they do, and you have, let's say, for 4 days of the week, you have things done all but one of those days, then if the reason is reasonable, if it's explainable, if it's justifiable, and that I can't argue one way or the other until I hear it, but a reasonable excuse, something that's beyond your control, then you do the problems in the book. Okay? You do the problems in the book. You do it on that folder, that binder we're talking about, and you check your answers in the back of the book. And you indicate how well you did. And I expect Loretta then to sign off on that the same as if you'd done it in the computer. And you just let me know what. Otherwise, if there is a problem, talk with Loretta, talk with me, and then I'll give you the credit for that as part of your average for your homework grade. Okay, because the computerized instruction is not giving me the flexibility if there are problems. And there's sometimes problems you just can't deal with. Life is that way. So I'll try to be as flexible as I can that way. At the same time, you understand, that means there's still, when you can, you should be doing the computerized homework. This is in those cases where you just couldn't do it. The life was such that you don't have access to that, and it's not to make that punitive. Okay, now, at this point, I don't want to talk about that much beyond my general statement. Now, this week, I'm still trying to put Humpty Dumpty together. In the sense, there have been all sorts of glitches. We had a number of people who weren't here yesterday or the day before. And again, just a reminder, the commitment, not so much of just what this program's about, but the commitment you've got to make. You've got to be in class and go through the material. You have to spend minimally an hour a night and more likely 2 hours a night in the material to make it happen. That's the commitment I want you to be making mentally. Without that commitment, it's not going to happen. Now, if there are individual problems, we'll try to help make that up. Now, some of you, for reasons which are defensible, didn't get the quiz on the makeup. Okay? I want you to see me on an individual basis. You know what you're responsible for. You're responsible for the 11 properties. I only ask you to know 10. If you will see me individually, I'll try to address that and give the opportunity so you can do that and not lose the points. But I don't want to do it right now, after class, if you would. And as I say, I would like to entertain, in a way, questions right now, but I don't think we have the luxury of that with what I still need to cover. The test is coming up. It is a week from tomorrow. Okay, that'll be in the first couple chapters, and maybe a little bit of 3. So that's where we're headed. Okay? So I'm hoping that we have sort of a sense of what's necessary. We'll work together on it, and talk after class if necessary. Of course, I've got another class within 7 minutes when we shut down here that I've got to go to. And as I say, I'd like to talk individually, but it can't be right after class, and I don't want to carry this discussion any further right now. I need to get into new material. So now let's go back to the mathematics. Are there questions from the homework you worked with in which we were doing subtraction, right? Are there any questions with that? I'm going to address one that Kim asked, but I'm going to ask first, are there any other questions on the homework with subtraction? Okay, then let me give you the question Kim raised, because it's one that I think I can explain through the properties, but I'm going to put a number on the board, an expression, minus 3 minus 5. So that's what I'm going to do, Jonathan, on the board behind me. So minus 3 minus 5. Well, maybe I will if I can hold on to the chalk. Now, we are supposed to trade this in for what? An addition problem, right? So the argument is one of these signs gets changed. So this is the one that we change to the addition, because in essence, this problem was asking you to do this subtraction, okay, in which this was really considered subtracting a positive 5. Now, the rule, we talked about this yesterday, the rule that many of you, if you've worked with sign numbers before, is you change this from a positive to a negative and you add. Okay, so this, in essence, is precisely what we're doing up here, where we argue in a general way. The argument is that if you have an expression, a minus b, and a can be negative. We talked about that yesterday. A can represent a negative value. And if you didn't get to see yesterday's presentation, and you didn't watch it on television at 3 o'clock yesterday, it is available over in the library at the reserve desk. So anything you've missed, you can go over and watch. Okay, so at the reserve desk, you just ask for yesterday's lecture in Math 20. Be in a VHS tape, and you can sit down and watch it. It was an important day. I mean, what we did yesterday was a very important day to watch. So if you didn't get to see that, remember this means that you changed that subtraction into an addition. So the rule is, and this is where you get a verbal statement, change the minus to an addition and take the additive inverse of the number you're subtracting. So you're subtracting b, so you change it to the negative of b. That's called the additive inverse. So up here, I'm going to take this and rewrite it as minus 3 plus a negative 5. Now, at that point, I realize the addition of two negatives will be negative. I'll get a negative 8. So I can rewrite that as a minus 8. Here, if I followed this rule, remember this is a sign of operation, not a negative integer. So it says change this positive 5 to a negative 5 and add. Well, negative 5 and negative 3 will be the same negative 8. There's a phrase we talk about when you get into discussions of how you learn things, and they are called misleading visual cues. Misleading visual cues. You've been trapped by them before. For example, you see a 3 and a 2 up here, and the misleading cue is you see a 3 and a 2 together and you think you should either take 3 times 2 and get 6, which is wrong, or you think that that maybe is 3 plus 2. You forget that its location tells you that it's a 3 multiplied by a 3. But that's misleading. Now, what's the misleading cue up here? Your focus is on this minus sign, right? But there's what? Another minus sign. If you do something here, why haven't you done it there? That's the misleading part. Because when I write it as a minus b, you don't see the negative sign. If a is smaller than 0, to the left of 0, you still write it as a. It just represents a negative number. It's misleading because you see it and you feel like you should do something about it. I think that was Kim's comment, that it's there. Shouldn't I do something to it? I did something to the other. Minuses are bad. That's sort of a philosophical thing, economy. Sandra.
So what you're saying is to replace negative 3 with a can represent negative 3.
I'm just saying that in terms of this expression here, this was a, which happened to be a negative 3 in this case. This b happened to be a positive 5. But when you see this expression, you don't know whether a is positive or negative. It represents a number, any number. At the moment, in this chapter, an integer. Okay, and we're back. Okay, I asked you in a Math 10 class to write down a number for me. That was one of the things we did. And if you'll recall, nearly everybody writes down a 7 or a 3 or a single digit, and it's a whole number. Rare that I get a negative number written down. Very seldom a decimal. Hardly ever a fraction. Because we aren't all that different than if I walk up to a young child and say, give me a number, and they'll say 5. Why? Because they're that old. Or you walk up to somebody and say, what's your favorite number? And a 6-year-old will say 6. A 7-year-old will say 7 because their age is such a focus for them. Their idea of number doesn't change a whole lot from that all the way up to graduate school. If I walk up to any of you and just say, give me a number between 1 and 100, you are most likely to give me an integer. You really have to be in a rotten mood to say the square root of 5. Or pi. Those are good answers, but that's not where your head is. In the same way, now this is where, coming back to Kim's question, you see the a, and you think positive because there's no minus sign in front of it. What we talked about yesterday was that if a is less than 0, meaning it represents a negative number, then if that happens, remember we had this big if here, then our statement was that the absolute value of a was equal to minus a. And that looks too much like a 9. And that's looking like a mess. Hopefully those a's look enough alike that they pass. This minus a is a positive value, but you see this minus sign, and what's the misleading cue? Anything minus is negative. That's the misleading cue. But a was negative, so its inverse is positive. Those misleading cues are just really trouble right now. And this was the crucial point I think we had trouble with yesterday. So I hope that answers your question, Kim, and relates to a few other things. Are there any other questions from that chapter section, or is there anything, Rita, that you've been asked about that we need to review, or anything that comes up?
No, the computer just was put parentheses around it. They understand do the additive inverse, but it took parentheses around it in order to show the separating.
So if you had an additive inverse, they would like you to do this on the computer because that's to illustrate that that negative 5 is really an integer and it is the additive inverse of 5. And you were able to type in without it and it accepted it. Okay, good. So, but again, that's what the text is doing. It's saying put it in parentheses, and it's trying to emphasize what? That minus 5 is an integer as opposed to the operation which was subtraction. Michael. Okay, so either way it goes in. A forgiving computer. Okay, Dion. Can you give me, when you say something in front of it?
If it was plus 3 plus, or if it was plus 3 minus 5 or whatever.
Okay, so we had this. You typically wouldn't write the plus sign, you just say 3.
Well, wouldn't that still be minus?
No, whoa, that's back to Kim's question. This doesn't change. Whatever it is, you leave alone. We're saying we rewrite this as 3 plus negative 5. And that was exactly what Kim was asking. You don't touch the left part. Down, okay, yeah, we're still seeing it. You don't do anything with A. It stayed the same, right? It's only you change the subtraction to an addition of the additive inverse of B.
So you only switch the second.
The second one, yes, and that's it.
The second one will have
Okay. Now, let's see how you want to say that. You say, if I had, let me do this. I think that's getting to your question. Let's slide over just a little bit for me, Jonathan, if you will. Now, I'm going to change this, right? That gets, no, you have to change that to addition. So that becomes plus, and then that says take the additive inverse of minus 5. The additive inverse of minus 5 is 5. And so this gets translated into 3 plus 5, which is 8. That just write down and come back to it, because missing that, it's going to be a little bit too fast right now. So write that down and come back to it, okay? So this is sort of like Field of Dreams. Write it down, they will come. And if not, you can ask questions about it later. Okay? Again, if you think of this now, and it's this one, let's see, what am I, right here, this one. Okay, this breaks it into two different problems. This one here. Let's go back to the Austrian method, because that's always a way of looking at this. I had a 3, and I wanted to subtract a negative 5. Now, remember I'm going up this way. How do I check? Well, how do I do the Austrian method? I ask you, what do I have to add to that negative 5 to end up with 3? Thank you. Nicely done. The 8. Okay? Well, that's exactly what I'm getting by changing this to an addition, and you do what? You change this sign. If I go back to the old rule for subtraction, change this sign to a positive and add. 3 plus 5 is 8. Well, when you took the inverse of negative 5, it's 5. Just think of the number line. My number line is centered here, and I'm out here at 5. Well, for you it would be, I think how you're looking at it. You'd be out here. Okay, as you're looking at me. You'd be out here at 5. Okay, the inverse of 5 is over here, minus 5. Okay, now I'm over here at minus 5. The inverse of that, called minus minus 5, is over here. It just flips you back and forth across 0. Okay? Any other question there? We're okay then. Okay, now, the next section, in some ways, is, I think, easier than subtraction. And we talked about yesterday how you look at a pattern. So, for example, the pattern was this. And this is the way it's usually done. You say, I want to show that a positive times a negative is going to give me a negative. And so this is supposed to be the convincing argument. This is supposed to just blow you away. You couldn't argue it because it seems so obvious. Not necessarily true, but that's the intent. So I say something, well, let's take 3 times 3. And I'm going to use an x for a moment, even though we use the x for what? A symbol to represent a number. But I'm thinking of it in this sense. We do these multiplications. By the way, we had a name for these. These were the multiples of 3. And so you said this was 3, this was 6, this was 9. And we usually think of going up that way to get multiples of 3. That's how we found common denominators, one of the techniques. Well, if you come down this way, the next obvious thing is 3 times 0. Well, you know that's going to be 0. Let's slide over a little bit, please, Jonathan, please. A little bit there. Now, we see a pattern going, right? 9, 6, 3. You drop 3 each time. So if the pattern makes sense to you, and I take 3 times now dropping this by 1, then the argument is this should seem reasonable to you. That's the argument. Now, if that doesn't make sense to you, then say, well, what does multiplication really mean? It's repeated addition, correct? To repeat the additions. So that means I have minus 1 plus another minus 1 plus another minus 1, which is minus 3, and that may be more convincing. That works real well as long as one of them is positive. It's when you play this game that it starts getting a little more find the pattern rather than repeated addition. Because remember, this 3 in front says repeated addition. Now I'm just dealing with a negative 3 times first to 3. And so the argument here is, well, we understand that would be negative 9. We have no trouble there. This is negative 6, negative 3. This is 0. And I hope it makes sense at this point that if the pattern follows, that's got to be a positive. Watch the monitor if I'm in your way. Now, what was my argument? If that doesn't convince you, then we're really back to something like this. If I take negative 3 times, say, and I'm going to now use parentheses if you don't mind, we know that 0 times anything is supposed to be what? 0. So I could do a problem like this if I'm trying to show this, what I'm pointing to, that negative 3 times negative 1 is 3. I could say, well, let's look at what 0 is. I could write 0 as 1 plus negative 1. Now that's supposed to still be 0, correct? Now what? Multiply the distributive property. Negative 3, and I'm going to use the parentheses, 2 of them together. That means multiply. Plus negative 3 times negative 1, and that's supposed to be 0. I need to just walk over here. Next step. By knowing that 1 times negative 3 has got to be minus 3. That's the identity for multiplication, correct? 1 times negative 3 has to be negative 3. Now, what do I have to add to negative 3 to get 0? Has to be a positive 3, correct? So if this is true, that's what this came to, there's no choice but to argue that negative 3 times negative 1 has to be positive 3. Now that's just for one number. But understand I could do any number that way, and I could make that a general kind of argument. That's supposed to be the motivation, the convincing argument, that a negative number times a negative number must be what? Positive. And so we sometimes write it this way as I slide over now, Jonathan, that if I have a positive times a positive number, that this is supposed to be what? A positive number. Well, that's our usual multiplication. And if I have a positive number times a negative number, we're arguing that that's supposed to be a negative number. Now, because of commutativity, I could argue a negative times a positive. And then the other case is what? A negative number times a negative number, and that's got to be a positive number. So the argument is this. When you multiply and they have the same sign, positive. When you multiply and they have different signs, negative. That's it in a nutshell.
Is that only for multiplication, though? Because addition is adding.
Okay, Richie's question is it only for multiplication? And the sort of caveat to that was, because in addition, it doesn't work that way. Yes, if I'm only thinking of multiplication and addition, it only works for that. But here's the nice perk out of this. What we just said for multiplication works with division. Again, let me say that one more time. Richie's asking, does this only work for multiplication? And you're setting up a kind of false dichotomy, that we only have addition or multiplication. If that's the case, then my answer to you is yes. And I have argued that in algebra we only have what? 2 operations we worry about. Multiplication and addition. But we still think of, okay, divide 5 into 15, and you answer 3. So I think of a division problem still. So what happens if I divide a negative into a negative? What will I get? And the answer is positive.
We're talking about addition.
No, I understand what you're asking. But you ask the question, is it only work in multiplication? This statement, a positive divided by a positive will be positive. A positive divided by a negative will be negative. A negative divided by a negative will be positive. It works exactly the same set of rules for multiplication and division.
Yeah, I knew that.
Okay, then my answer to you is yes.
I mean about the addition, because a positive plus positive is a negative, so I would
Whoa.
ask,
Yeah, you want to rethink that, right? Sometimes. What Richie's saying is a positive added to a negative is a negative. Not always. Let's look at some cases. Just down here. So slide, yeah, that'll be okay. Slide over here. Let's say a positive plus a negative. So here's a 3 plus a negative. Now this time it comes out negative, correct? But I could say 3 plus minus 1, and this time it comes out a positive 2. It doesn't always come out the negative. Sometimes positive, sometimes negative. True? If you have negative 3 plus a negative 2, it's going to be negative. So if you add two negatives, you get a negative. Okay, if that's what you were saying, I agree with you then. A negative plus a negative is negative. But a positive plus a negative can be either way, depending on the numbers. And that's what I thought you were saying. So, okay. Out of these two? Right, but here I would. Okay, we're in agreement then. I think I agree with you. Michael.
I have a problem. Negative 2 to the 4th power.
Okay. Yes. This is where things get just a little bit dicey. The question is, negative 2 to the 4th power. Now what Michael said I can hear in two ways, selectively. I could have heard this, or I could have heard this. And the answers are not the same. No. I know what you meant. I was pretty sure I knew what you meant. But this is possible also, because what Michael said was consistent with the first one. Minus 2 to the 4th. This should have said the quantity minus 2. The quantity means put in parentheses. To the 4th power. Now this one has to come out positive. When you multiply two negative numbers together, you get a what? A positive. So, okay, I'm going to have to travel. I'm out of space. So, are you in camera 1 or 2, Jonathan? Go to 1 for a moment, please. I need more space to talk about this. This is the important problem of the section. The important problem of the moment. Okay, so, okay, camera's there. We'll leave that on task, and I'm going to come over, and don't go there yet because I need to erase some things from statistics. That was a nice bell-shaped curve. Hate to see it go, but it has to. Okay, now, what we're contrasting as we come to the sideboard is negative 2 to the 4th versus, in parentheses, negative 2 to the 4th. Now, when you verbalize it, they sound very much alike. Without this parentheses, this says take the additive inverse of 2 to the 4th. This is the same as this. I'll take that back. I'm going to do it this way. That's what it's saying. The additive inverse of 2 to the 4th. Now 2 to the 4th is what? 16, agreed? Yes. That's 2 times 2 times 2 times 2. So this is negative 16. What does this mean with the 4 outside the parentheses? No, but first, what does it mean? Okay. Sandra's saying it right. You write the factor, the base, 4 times. So that's negative 2 times negative 2 times negative 2 times negative 2. Now, you aren't canceling anything out. But you're saying by pairs. So thinking of breaking this into 2 pairs. Then this comes back to Emily's question. The first 2, when you multiply 2 negatives together, must be a what? A positive. Okay, when I multiply these 2 negatives together, I should get a Positive. So what's a positive times a positive supposed to give me? A positive. Shortcut time. If this is an even integer, you'll get a positive out of this. Whether it's 6, 8, 12, 100, you're going to get a positive answer. If this is an odd integer, 1, 3, 5, 7, 11, 9, 13, 101, you will get a negative. Because an odd number of negative multiplied together will give you a negative. An even number of negative numbers multiplied together, bless you, will give you a positive. We got it? So this one's going to come out positive 16, whereas this said you had the additive inverse of 2 to the 4th. Well, 2 to the 4th is going to come out positive. 2 times 2 times 2 times 2. And then take its inverse. Okay, Michael.
So would the opposite of the shortcut you just gave us apply to the first problem?
The opposite of the shortcut apply to the first problem. Explain for me.
If the exponent is even with the negative integer, it's going to be...
I see you. Okay, what Michael's asking, let me come back here. I said if this is even as an exponent, this will come out positive. If this is odd as an exponent, it's going to come out negative. This, I don't care whether the exponent's even or odd, you'll still get a negative when you're done. Because you're only, that 4 is only telling you the base is written 4 times. So this, in essence, said you had negative 2, dot 2, dot 2, dot 2. The base for that exponent is what it's immediately attached to, which was the 2. To force this, that my base was negative 2, I had to have the parentheses. Now, this is for fun. General statement. Now, negative a to the second is just going to be a squared. Because that's negative a times negative a. The negative times the negative comes out the positive, and you get a to the second. This stays the inverse of a squared. So this will turn out to be a negative number. Whatever a is. Minus a squared will be less than 0. This, whatever a is, will turn out greater than 0. Now, if you're feeling comfortable with using a to represent numbers, that should be something that works for you. So I'll just say minus a squared has to be less than 0, whereas a squared has to be greater than 0. Now this assumes, for the moment, that a is an integer. By the way, it will work for a as a fraction or a decimal. It won't work for that case where we talked about square roots, and I commented to you, and this is just a kind of for the future, back to the future. Remember we said you're okay if you take the square root of a positive and you get a 3. But if you take the square root of something like minus 1, there's nothing at the moment in the set of integers or fractions or decimals that works. And we then get what we call the imaginaries, and we call that little I. Now when that is done, and we expand our number system to what are called the complex numbers, this becomes negative 1. So my point being, the real numbers having an a squared has to be positive. But if we go further, and we will in an algebra course, we'll allow this to happen, then we get positive, well, an I squared, no longer positive, coming out negative. So that's in the future. Okay, so I is the square root of minus 1, and I squared is minus 1. This is an I number. There's I max, I phones, and I numbers. Okay. Other questions? Okay, before you come up with a question, I'm going to go back center and look at the book. Folks, in a lot of ways, what we're dealing with now, in my sense of the word, is the jargon, the language, the set of numbers we're working, and these are the ground rules. And I'm going to make a statement here I hope that will help a little bit. One of the things that children do is learn new games. And sometimes adults, we also are asked to learn a new game. Somebody wants to play a card game, and you don't know how to do it. You say, okay, explain to me the rules. And they say, well, watch a couple of hands. And you'll learn, and then jump in, and then after you've made about 5 mistakes, you get a better feel for it. So you learn the rules, right? And then once you learn the rules, things smooth out, and you do pretty well. So it's a little bit like a game. And so what we're learning are the ground rules. What happens when you do certain things to numbers and you have 4 operations to worry about? Addition, subtraction, multiplication, and division. And that's what we're doing with signed numbers, as they're called at the moment. We're restricting it to whole numbers and their negatives. Now, pretty soon we have to do Emily's property and work with the fractions. And everything we've said for integers is going to have to be true for fractions. And then we're going to say, okay, now we need to go past fractions because not everything can be written as a fraction. The square root of 2 can't be written as a fraction. And that will be then a case where I will have a situation that I extend it to what's called the real numbers. Okay? That's where we're headed. Each one's a new chapter. And the idea eventually is that we finish the real numbers, and then you're ready to go on into algebra. And if you know it all, it'll go smoothly. And there'll be some glitches, and keep in mind that, and I think this is something to put in perspective from the last quiz we did. Not the one on the properties, but where I gave you something out of the orange book and said, can you find the area in this diagram that looked like a half circle, a triangle, and a rectangle, like the letter P from PBS? You found that you had forgotten some of that. And so what's the difficulty always? That you forget things. Retaining the information. And to go back, and so what you find in a pre-algebra is you remember some of the things that you forgot in the pre-algebra. And then when you take the algebra course, some of the things we did here will make more sense. So the key is never quit. Go from pre-algebra to intermediate algebra, and the other course that you just finished will always be clear. And after 4 or 5 years, you have a major in mathematics, master's degree, and there'll still be things that if you do a doctorate will get clear. Isaac. The question is, will I be teaching 70 next semester? There's always a 70, but it's a video-based, which means 60 hours of lecture online, 24/7 access, and some people enjoy doing that, and some people don't.
So you can go home and watch it and do it your homework?
Yes, you could go home and watch it and do it your homework. The danger, going home, not doing it and not watching it, because there are 6 other things that are more exciting than watching that video at the moment. So it is not quite the good thing. Talk to Rita about it. She's doing it. Now, going on to material in this section. Okay, this is on multiplication. It is section 2.4. And it is actually, if you'll note the title here, as I bring this up, everything we've said about multiplying should hold true for what? Dividing. And when we take square roots, okay, we've just commented as we come off there, that if you take the square root of a positive number, you're going to be okay, but we're restricting that to perfect squares at the moment. So like the square root of 9 is 3. So to that degree, there isn't a whole lot here that we haven't already said. The one that Michael just asked about, for your information, is on 127. So let's look at that. This was a warning, meaning danger ahead. I'll try to bring that down a little bit tighter. That's on page 127, and we just talked about that. Okay. Now, while I'm at it, let me do another comment here, because, and I don't know if this is covered there, but it should be. What about this? That's the absolute value of negative 2 to the fourth, correct? So the absolute value of negative 2 is 2, still to the fourth, and that comes out 16. But notice that's slightly different, because this doesn't mean you're taking minus 2 times minus... Back it up a little bit more. Thank you. You were thinking where you want to be. Minus 2 times minus 2 times minus 2 minus 2. This says you're going to take the absolute value of negative 2 to the fourth, which really meant you had 2, dot 2, dot 2, dot 2. That's just in passing. I had a question regarding that from somebody or not? We okay?
Yeah.
Thank you. Okay, coming off there. I need rapid transit between these two spots. Now, coming back to here, the dividing of integers. And the comment, I guess, is that they're done the same. There's an illustration there, but let's just look at two parts. The first two up here in example 6, I'm on page 128. You understand that a division can be done in two ways. This goes back to Math 10. So I can think of it as written in this way, minus 45 divided by 9. That's the division, I guess, in a sense without using the short division symbols, but that comes out negative 5. This one, a fraction, means a division. So what I'd like to do there, just as a comment, and I'm going to try to get this page so it'll stay where I have it with some support. Okay, and I'm going to go back to the side. Leave that up there for a moment, Jonathan. We don't typically write the problem the way I'm going to do it, but you could. I could say I have a 9 into, and let's go to the board. We just never do that. But it's understood. And the reason I do that for the moment is if you say this is negative 5, how do you check this? You multiply these two together. So if you take a positive number into a negative number, this would have to be negative because the only way you can get a negative out of this product, the 9 was positive, that has to be negative to get this. And we don't usually write it that way. What it was given to you was this way, but that is an implicit fraction of negative 45 over 9. You still get the negative 5 each time, and that's about all we need to say of the rules for multiplication and division are precisely the same, which is what Richie was asking about. Now, this is no order of operation. This just says if you are dividing, and this is 3 different ways of showing division. When you divide, okay, let me come to that in a moment. Let me leave this. And what Isaac's talking about in order of operations, I assume, and you do them whichever comes first. So if you have a division first, you do it. If you have a multiplication first, you do it then as a first. And the order of operations don't occur yet, I believe, in this section. That's correct. So things are very straightforward. Probably the only thing that needs to be talked about here, and this is a little addendum back to the book. This is on page 130, and this is where I need to say just a small bit of information that we haven't. In the problem, I'm going to go to the first one written, the square root of 144. You understand that's a perfect square as I go to the board. 12 times 12. So the square root of 144 is just a positive 12. Now, what I'd like you to understand also is that negative 12 times negative 12 is equal to 144. So the question is, since both these work to the same number, both of these are 144, what did I want you to get when I said take the square root of 144? If I don't put anything in front of that square root symbol, it is expected to be the positive answer. But if I want the negative answer, I put the negative sign in front of the radical, and that answer then is negative 12. Hold on. If you don't see anything in front of the square root symbol, that is called the principal root. So we talk about the principal or main root. So principal root, and I warned you before, that's dangerous to say root because I could have a cube root. I could have a fifth root, so it would be better to say principal square root. If you want both, you put plus or minus in front of the radical sign, and then that is plus or minus 12, and there will be a point in algebra where that will be important. Okay, we are going to get an expression, and I'll just show you where this comes up. We're going to get an expression in which we're going to have minus b, meaning the additive inverse of b, plus or minus the square root of b to the second minus 4 times an a times a c, and that's going to be part of an expression, and notice the plus or minus. It'll come in there. This happens to be solving for a solution to an equation. I don't have the full solution, but that's just part of the mess that you would see. Yeah, that's algebra. It's the good stuff. Okay, I'm going back up front. Let me hold on. I'm watching the clock here very carefully because I want to make sure what else is said. At this point, the comment, okay, back to the book. Here's the square root of a negative, and all that's said for the moment is it's not an integer, folks. It's not a real number. Otherwise, that's only half the answer as I come off there. The square root of negative 36 not only is not an integer, it's not a real number. No, it's not negative 6. What's negative 6 times negative 6? Positive 36. So you couldn't multiply, but a square means you multiply the same number by itself. So it couldn't be negative 6 times positive 6. It DNE does not exist. So we extend to what is called the non-real numbers called complex numbers where you have little I. We get the I number. Rules. Yes? No, not the little I. It's not theirs. Page 130, the rule. Notice the principal square root. Then this is the additive inverse of the principal root. So you can get a positive or negative. We have to indicate which one we want. And it says the square root of a negative number is not an integer. Just replace that. Is not a real number. Does not exist. You're in trouble. Okay? Now, coming off there. Dion, you had a question. Yours was next.
Yes, well, it's kind of off a little bit. I want to know, would you ever, like how you did the negative outside the square root of 144?
Yes.
Would you ever have an index number over that square root?
Okay,
like negative?
okay, let me come back to that problem. I'm going to the sideboard again, please, if you would, Jonathan, just in space. What Dion's asking, would it be possible that you would have a negative in front with an index? So let me do this one. I'm going to have a negative, the cube root of 8. Okay, the cube root of 8 is 2. So yes, that would be a negative 2. Okay. The 3 means it's called an index, and it means you want some number you can multiply as a factor 3 times. So it says I have to have some number. A times A times A has to equal 8. Well, what number could you put A? If a was 2, you would have this, so the cube root. That's beyond where we were, but the argument is there's a danger to keep saying just root of something, and I have to be done. Okay, we're going back to Fleetwood Mac, and what's